Hey everyone, welcome back. So we're going to be talking about the heat treatments of steel. Now, I do want to make it a point to say that when we're talking about heat treatments here, I'm only talking about carbon steel. So low carbon, medium carbon, and high carbon. While stainless steel is still technically a type of steel, there are some things in this presentation that could apply to stainless steel, but I don't really want you to be thinking about stainless steel. We're only talking about actual carbon steel. Low carbon, medium carbon, high carbon. Alright, with that said, let's keep it going. So why do we heat treat metal? Why do we spend the time to heat metal up for prolonged periods of time or for short periods of time and cool it rapidly versus cooling it slowly? Well, as we're doing this, we're changing the mechanical and physical properties of steel. And so those properties are the following four: hardness, brittleness, ductility, and strength. And there are various methods that we can use in order to heat steel up. We can either use a flame where we're using compressed gases to fuel the flame. We can apply that to the steel to heat it up. We can place the steel in an industrial-sized oven that is capable of reaching high temperatures, or we can also use induction coils. Either method doesn't really matter. The only thing that really matters when choosing the method to go with sometimes falls into how big your part is, because induction coils can only be used with smaller pieces of steel. Torches can be used for bigger pieces of steel. And then, of course, if you have an industrial-sized oven, you can probably fit anything in there. So the very first type of heat treatment that we'll talk about is quenching, also known as hardening. So when you harden something, you're taking a piece of steel that is around its transformation temperature, and then you're cooling it off rapidly. So this is either by dunking the metal into a quench tank that's filled with water. It could be filled with oil, or you could be burying it in a barrel of sand, or you can be hitting it with a high stream of compressed air. Either way you do it, you're still accomplishing the same thing. You are cooling the piece of metal down very rapidly, and this is causing the steel to harden. So what happens when you harden steel? Well, actually, let's backtrack a little bit. Let's talk about what happens when you heat steel up. So if you remember from a previous video, when you heat steel up, you're opening up the grain structures. You're changing the structure from body-centered cubic to face-centered cubic. Now, when you're taking steel into a place where it's face-centered cubic, that's allowing for more carbon molecules to fit in between the iron molecules. And if you don't allow the steel enough time to cool off at a normal rate, or basically cooling off by itself, that's going to trap those carbon molecules within those grain structures. And when you do so, you're turning the steel into what's called martensite. Now, when you turn steel into martensite, you're increasing the hardness, but the downside is you're also increasing the brittleness, and you're also decreasing the ductility. So there are some drawbacks to quenching, but there are also some upsides to quenching, because there are times where you want your metal to be hard. Let's talk about annealing. So annealing is when we're taking a piece of metal that has already had some shape or form of heat treatment applied to it, and you're basically bringing it to its most softest state. So you're heating a piece of metal up to its transformation temperature, and you're going to hold that over a certain period of time, and then you're going to control the rate at which it cools off. So this isn't just applying heat using a torch or applying heat in an oven and then just cutting it off. No. This is heating it up to its transformation temperature, keeping it there for a little bit of time, and then we're slowly turning the heat down. Now, depending on what exactly you're trying to achieve, you could control the cooling rate to a matter of hours, or you control the cooling rate to, say, something like overnight. It just depends on what you're trying to do. So remember, annealing, you're heating it up, keeping it there, and then you're forcing it to cool down slowly. Now let's talk about stress relieving. So I mentioned stress relieving because it's very similar to tempering, and a lot of times people will confuse the two, stress relieving and tempering. So stress relieving can be done to metals that have not been quenched. So they haven't been really hardened. So this happens in cases where you're welding things. In this image we have pieces of pipe, and in order to prevent the weld site, not just the entire piece of metal, but just the weld site, in order to improve the ductility, improve the strength, but also retain some of the hardness, they'll put warming blankets that have these coils that wrap around them and produce a little bit of heat, sort of like an induction coil, but it doesn't produce the same amount of temperature. What this does, it applies a little bit of heat to the welded area to relieve stress. This is going to prevent cracking later on. This could help with distortion. This is going to allow you to keep all those mechanical and physical properties that are ideal for a finished weld. Now let's talk about tempering. So tempering is when you're softening a metal that has already been hardened. So remember, when we're hardening a material, we're putting that piece of steel into a position where it's now martensite. So the brittleness is high, its strength has been decreased, its ductility has been decreased, but its hardness, of course, has increased. So tempering is a method of heat treatment that we would apply to a piece of steel when we want kind of the best of both worlds. We want to keep that hardness, we want to keep that strength, but we also want to keep our ductility. We want to reduce brittleness. A perfect place to see where tempering is used is in blacksmithing, or more specifically, bladesmithing. So kind of jumping to the forged in fire example that I gave in a previous video. When you harden the steel that you're using for your blade, you're hardening it because you don't want your knife to break. You want it to be able to, be hard, be able to pierce things, but then you also want to temper it. So that way, if you're kind of moving it around, you're using it to cut something tough, or maybe you're in a position where you need to strike an object with your blade. You don't want that piece of metal to shatter in a bunch of different pieces. You don't want to be in a position where you're bending this piece of metal and next thing you know, it breaks. So by tempering a piece of metal, you're softening it up so that way you can get some of that ductility back. You can reduce the brittleness, but still maintain your hardness. And so how we temper a piece of metal is we heat it up to a point that's below the transformation temperature. So we're not heating it up all the way to its transformation temperature. We're heating it to a point below that. And then we're going to stop heating it and allow it to cool by itself, or basically cool in a room temperature situation. And so if we look at this image, you can tell it's been tempered by the coloration of the steel. So if you see kind of like these blues, purples, grays, so this is a key indicator that the piece of metal that you have in front of you has had heat applied to it in a way to temper it. Now the last form of heat treatment is called normalizing, and the name should kind of give it away. This is a heat treatment that's applied to metal in order to bring it back to its original state, or as close as possible to its original state when it was received from the manufacturer. So this is used if a piece of metal has been hardened, or it's been tempered, or maybe you don't know what's happened to the metal. Maybe you've got a piece of metal that looks like someone worked on it before, and so you're not quite sure what its treatment is. You can go ahead and put it through a process of normalization. So you can take this piece of steel, you're going to heat it up to its transformation temperature. So remember, in tempering, we're not going up to its transformation temperature. We're going below it. With normalizing, we are taking that piece of steel to its transformation temperature, and then we're going to cut the heat, and we're going to allow this piece of steel to cool off by itself, basically air cool, and we're going to do so in a room temperature area. So when we're normalizing something, this is where we're reducing hardness, we're reducing brittleness, but we are gaining ductility, and we're certainly gaining strength. And here are a couple scales that a lot of people use when they're gauging temperatures. So the very first one down below is your tempering scale. So after a piece of metal has already been hardened, once you kind of grind or sand the surface to shiny metal, you can start applying heat. And then depending on what color the steel turns, you can use that as an approximation of how hot the steel is. Of course, it's not always going to be exact. It's always good to have another method of measuring the temperature of that steel, but you can use this to kind of ballpark it. So we can see that a piece of steel on the very left at room temperature, it's just normalized. Or let's just go ahead and not say normalized. Let's just say you brought the metal down to shiny bright metal. You're starting to heat it up. Right around 350 degrees Fahrenheit, it starts taking on sort of a straw color, like a very light yellow. And then as you start increasing the temperature, it goes into like a dark yellow, sort of like a yellowish orange, and then a burnt red, and then into a purple. And when you start increasing the temperature even more, this is where you start seeing like the blues. And once you get it really hot, you start seeing a gray appearance. Now this is where the temperatures kind of stop for tempering, because if we use this other scale up here, you'll notice that once we get past 730 degrees, let's say, where's it at? Well, it ends over here at 630, but let's say we get to like around 800 to 1000 degrees. This is where it starts glowing red. So we'll have a dull red, and it starts going up in brightness up until it reaches a point to where we call it white steel. And this is just at a point where it's so hot, it becomes so bright that it's hard to look at without the proper filter shade lens. So anything over 730 degrees, or we can even say 630, anything over that range, 630 to 730, that is less tempering, more normalizing. So we need to know the differences in temperatures in order to achieve the appropriate heat treatment. So tempering, use this scale. If we're using something like annealing, normalizing, or heck, even quenching, this could be a scale that we use right here. Okay, so here's just some information out of a code book, and this all relates to heat treatment. I'll go ahead and I'll let you pause here if this is something that you do want to read into. There are just some definitions and some slight explanations. But if you want to keep going and just come back to this later, you're free to do so. Let's keep it moving. So this should look fairly familiar to you if you've watched one of my previous videos. This is the iron carbon phase diagram, or as some others will call, the iron equilibrium chart. And so just a brief recap on this. We have our temperature scale on the left, and on the bottom we have our carbon content percentage. This chart is used to kind of more accurately place your steel and its heat treatment, so that way you can determine what grain structure the steel has, so you know how to work with it. So the lower the carbon content, the higher the transformation temperature. The higher your carbon content, the lower the transformation temperature. And so this comes into play when you have a piece of steel that's at room temperature, and if If you know that it has not been heat treated already, this is something that's at its normal original state, and you wanted to harden it, depending on the carbon content, you would be able to tell what temperature you need to bring it to. You would bring it up to that point, up until the point where that steel is now called austenitic, or basically the steel is no longer magnetic. And you would let it sit there for a little while, and then you could quench it. And so what that does is it allows extra carbon to find its way in between the iron molecules. And then when you quench it, it freezes that grain structure. So this is putting the steel into a grain structure that we call martensite. So remember, this is where it's hardened, but its brittleness has also gone up, and its strength and ductility have gone down. Now, if you wanted to temper it, you again could find the carbon content of your metal, and that would tell you how hot you need to, or how high heat you need to apply to that piece of steel, bring it up to that point just below its transformation temperature, and then allow it to cool off. This would bring it back from a martensite grain structure to something like around ferrite or even pearlite, somewhere around there. Then if you wanted to normalize it, you can bring it up to a certain temperature and, just go through the various heat treatment processes. So this chart really comes in handy for people who are heat treating metal. Okay, so what's all this stuff that I'm talking about when I say strength, I say hardness, brittleness, ductility? What do these terms mean, and what do they do, or what does the steel do when we start using these terms? So if we think of the strength of the metal, if I were to take a piece of steel and I try to use my bare hands, or maybe I try to stick it in a machine, or maybe I'm striking it with a hammer and I'm trying to bend it, or I'm trying to pull it apart. Strength is the ability of the steel to resist it. So this is how well the metal keeps its shape when force is applied. And then hardness is how well the steel holds up when you try to penetrate it with something. So think of using a chisel or maybe a center punch. You're trying to mark the metal by putting little divots in the surface. So if you're trying to pierce the surface of the metal, hardness is how well it resists that. Now, brittleness is the ease of it's how easily the metal will snap apart or basically crack when force is applied. So same thing as strength. If you think about trying to hit it with a hammer or bend it with a piece of machinery or with a tool, if it's brittle, it's going to crack or break apart very easily. But if it's high in strength, then it's going to bend a little bit before it breaks. And then ductility is similar to strength, but it is how much you can bend or misshape or basically deform that piece of steel without it breaking or cracking. So let's take another look at strength. So in nice simple terms, strength is the ability of steel to resist deformation. So the image you have are of a couple pieces of steel that have been put through a tensile strength test. This is where the metal is machined into the shape that you see there, and it's put into a machine that it basically pulls it apart. And so you can see the piece of metal on the left, it looks like it's been stretched out a little bit. You see how it kind of tapers off. It gets thinner towards the tip. So this is when a piece of steel is ductile, when you're able to stretch it apart before it breaks. Whereas the piece on the right, it's pretty much the same width from start to the break point. So this is what happens when your piece of steel is brittle. Instead of stretching as you bend it, it just snaps or breaks. Hardness, simple terms, the resistance to penetration. So here we have someone using what looks like a center punch. They're probably going to mark out where they're going to drill a hole. So hardness is how well the metal holds up to something piercing the surface. And then we have brittleness. So remember, brittle, when a metal is brittle, instead of bending or getting drawn out as you start to shape it, it's just going to break immediately. So take these pieces of metal, for example. So these came out of what's called a Charpy V-notch test, where a little V-notch is kind of machined into the side of these pieces of metal, and then they're more or less smacked with a hammer, and this machine that controls the hammer records how much strength it took to break these pieces, or if it held together, how much strength did this piece of metal withstand. And so if a piece of metal is brittle, it's going to break and crack a whole lot easier. And then we can take this knife down here, for example. This knife was probably hardened, but it wasn't tempered. And so if someone were to try to puncture something with this knife, it would lead to a break or a crack leading somewhere in the blade. And we can obviously see that it cracked and it just broke all the way through. And then we have ductility. So ductility is the ability or inability to be drawn out or bent when force is applied. So we've got some rebar here. This person is bending quite a few pieces of rebar all at once. But if you were to take a piece of metal and try to bend it, if it's small enough, you might be able to do it with your bare hands, or you might have to use a tool or maybe a piece of machinery. Ductility is when you apply force to either pull it apart or just mangle it. And so how well it holds its shape while not breaking, this determines how ductile it is. So just a little more about heat treating. It is a process. It's not something that you're going to be able to do in an instant. It takes time. This is something where you have to understand what's going on with the grain structure of the steel. You have to know the carbon content of the steel, so that way you can apply the proper heat treatment to it, depending on what you're trying to do. Now, I put this image up on here because this was a contestant on Forged in Fire, and this is just another application where heat treatment is a make or break issue. So just remember, as hardness increases, so does brittleness. But as hardness increases, ductility decreases, and strength also decreases. As you change one characteristic, you might be changing one or more of the others. So you just have to take your time, plan out what you want to accomplish with your heat treating, and then set out to do it correctly. Don't cut corners. Don't try to race through it. Take your time. And then I just have some other definitions here for you right out of the code book. Basically things that I already went through, but if you feel like learning and reading the word for word exact definitions of these terms, you can go ahead and pause it here, read over them. But this is basically it. This is heat treating in a nutshell. So I will see you in the next module.